In the last few lectures, we had derived the conservation equation for mass, momentum and energy in Cartesian coordinate system in one dimension, unidirectional transport and unsteady, that is there could be variations in time and in one spatial coordinate. So, the configuration generally was that we had some coordinate z perpendicular to two surfaces at say z is equal to 0 and z is equal to h, and there is some variation in the field variable between these two. Field variable, concentration for mass transfer, temperature for heat transfer and velocity in the x direction for momentum transfer. And the general solution that we had got for the field variable was of the form partial of phi field variable by partial t is equal to partial by partial z of the generalized diffusivity times partial of the field variable by partial z plus the source, okay, where the field variable is equal to the concentration for mass transfer, the temperature for heat transfer or the velocity in the x direction for momentum transfer. Note that for momentum transfer, the equation is written for the x momentum. Momentum in general has three components, it is a vector. In this particular case, we will consider flow in the x direction and velocity variation in the z direction. Okay. So, those are the field variables. The diffusion coefficients are the mass diffusivity for mass transfer, the thermal diffusivity for heat transfer and the momentum diffusivity or the kinematic viscosity for momentum transfer. Okay. And the source, the production rate is equal to the mass production rate for mass transfer, the thermal energy production rate by rho Cp, if you write the energy balance equation in terms of the temperature. If it is written in terms of the energy density, then it is just SE. Okay. And for momentum transfer, it is equal to the body force in the x direction divided by rho, where Fx is a body force density, force per unit volume. Okay. SE is an energy density, energy produced per energy production rate, energy produced per unit volume per unit time, and S is the mass produced per unit volume per unit time. Okay. So, those were the general forms of the equation. I should note that this applies for heat transfer when density and specific heat are a constant, and I had told you that in most practical applications the specific heat is actually a constant, and for momentum transfer when the density is a constant, that is when the flow is incompressible. Okay. So, in that case this general equation applies for mass, heat and momentum transfer. For the particular case where the diffusivities are constants, the equation is d square phi field variable by dz square plus s. Derivatives, note, are partial derivatives. Okay. So, there is a second order in the z coordinate, first order in time. It requires two boundary conditions and one initial condition. Okay. So, these are the general equations, and we started solving it for specific cases. Okay. The first was the simplest case where it was steady and there were no sources. Okay. If the equation is steady and there is no source, the field variable is a linear function of z. Okay. So, if I fix the value of the temperature at the two surfaces, automatically the temperature everywhere in between is just a linear variation, the flux is a constant. Okay. And the transport rate is equal to the flux times the area. Okay. So, the transport rate is also a constant. Okay. The field variable is a linear function of z. If we have multiple materials in a composite slab consisting of multiple materials with different heights and different thermal conductivities, you can use the analogy with the electrical resistance. Okay. The ratio of the transport rate, okay, the resistance is equal to the ratio of the temperature difference divided by the transport rate with a negative sign, because the transport rate is in the direction opposite to the temperature gradient. So, you can use this as the resistance. From Fourier's law of diffusion, this is also equal to h by Ka. Okay. So, you will have, for example, the resistance of the first slab is equal to h1 by K1 A1. The resistance of the second slab is equal to h2 by K2 A2, etc. And the total resistance is the sum of the resistances in this series calculation, in this series configuration. Okay. So, this is what I had demonstrated over here. Okay. If you have two slabs, you get two resistances, multiple slabs, you get multiple resistances. The total resistance is the sum of the resistances for this series configuration, where the current is the same, that is, the flux is the same, and the temperature difference is the sum of the temperature differences across each slab, or voltage difference is the sum of the voltage differences across each slab. So, that is the series configuration. In the alternate parallel configuration, the current is the sum of the currents. You have different pathways, different slabs. Okay. In this case, you have different slabs which provide different pathways for heat transfer. The total heat transfer rate is the sum of the heat transfer rates in each individual slab. The difference in temperature is the same across each slab. What that means is that the temperature profile is the same, because the temperature at the top and bottom is fixed, and there is only one straight line that can connect those two. Okay. So, that is the temperature profile. That is fixed. The transfer rate is different, because the thermal conductivity and the areas of each are different. And in this case, you get this inverse sum rule, that is 1 over the total resistance is equal to the sum of the inverse of the resistances of each of those. Okay. So, that is the parallel configuration. So, that is where we stopped last time. So, this is the simplest case when there is no time variation and where there is no internal source. Okay. Next, let us take a case where there is an internal source, and that is the viscous heating. So, we have a channel with the z coordinate perpendicular to the plates, okay, and this top is moving with a velocity v compared to the bottom. So, you get a linear velocity profile, okay, and the fluid has viscosity mu and thermal conductivity K, okay, and you get a linear velocity profile. Now, the question that we are asking is, what is the temperature due to this, okay, flow. If you recall, when we discussed heat transfer in a pipe, I had told you that we can consider the heat energy and mechanical energy to be two different quantities provided there is no interconversion of energy. Alternatively, if the rate of production of heat energy due to mechanical work is much smaller than the transfer rate due to thermal temperature variations. Okay. In that case, we can consider these two to be different dimensions, and that had simplified our problem. In case there is interconversion, then we cannot consider these two to be different dimensions. In that case, how do we calculate the temperature in a channel? Okay. So, in this case, I will assume that the temperature of the two walls is the same, T is equal to T naught, T equals T naught. Okay. Because there is flow in this, okay, there is viscous heating, and therefore, the temperature increases. And this is a common feature of all lubrication flows. Okay. Whenever you have, for example, a viscous fluid lubricating the gap between two solid surfaces, if those surfaces move at a relative velocity, there is shearing within the fluid, and that tends to increase the temperature within the gap between the two fluids. Okay. The energy source in this case, okay, the energy source in this case. So first of all, as far as the momentum transfer problem is concerned, right, it is a steady flow. So, therefore, the unsteady term is equal to 0. There is a viscous term, okay, and there is no body force acting on this. Okay. So, therefore, this just tells you that d square V x by d z square has to be 0, which implies that V x is equal to some constant into z plus b, linear profile for a steady state without any sources or sinks. Okay. And you can get A and B from the boundary conditions, that at z is equal to 0, the velocity is equal to 0, and at z is equal to h, the velocity is equal to v. The top plate is moving at velocity v, the bottom plate is moving at 0 velocity. So, you just apply that, and you will get this is equal to V z by h. Constant A is V by h, constant B is 0, you get a linear profile. So, this is the velocity profile. Okay. What is the source of heat energy? Okay. So, the heat energy generation per unit volume of fluid per unit time. Okay. Due to this flow, okay, the formula for that I will just write it here. S E is equal to mu times the shear stress tau x z times dV x by dz. Okay. The stress times the strain rate is the energy production rate per unit volume per unit time. Okay. Stress is energy per unit area, okay, and you are multiplying it by stress is force per unit area, okay, stress is force per unit area, which is the same as energy per unit volume. dVx by dz has dimension of inverse time, because velocity is length per time and z is a length. So, you are multiplying the energy per unit volume multiplied by 1 over time, which is the energy per unit volume per unit time. Okay. So, dimensionally this is consistent. We will take this as given and proceed. Okay. The stress is equal to mu dVx by dz from Newton's law. From Newton's law into dVx by dz. And dVx by dz can be obtained from this expression. Okay. So, the energy production rate becomes mu v square by h square. Okay. That is the energy production rate per unit volume per unit time. From this, how do we determine the temperature variation? Okay. The energy balance equation at steady state 0 equals K d square T by dz square plus S E. Okay. If I write this in terms of thermal conductivity, there is no factor of rho C p. If I wrote it in terms of the diffusivity, then there would be a 1 over rho C p multiplying the energy production rate. Okay. So, this is also equal to alpha yeah. Okay. So, therefore, I can solve this equation. Okay. D square T by dz square is equal to minus S E by k is equal to minus mu v square by k h square. Okay. Integrate 2 times and you will get T is equal to minus mu v square z square by 2 plus a constant into z plus another constant. Okay. And then we have to apply the boundary conditions. Okay. Note that the boundary conditions for the temperature at the two surfaces are that T is equal to T naught on both surfaces. Okay. T is equal to T naught on both surfaces. Therefore, okay, at z is equal to 0, T is equal to T naught implies that B equals T naught. At z equals h, T is equal to T naught implies that plus A h is equal to 0. Okay. So, that gives me the value of A. Okay. A is equal to minus mu v square by 2 k h. Okay. And I can collect those terms to get the final expression T naught is plus mu v square z by h square. Okay, that is the temperature profile. Okay. That is the temperature variation across the channel, and you can see that this is a parabolic profile. Okay. The temperature, if I look at the temperature across the channel, I will get a parabolic profile. Okay. T as a function of z. Okay. It is equal to, or rather let me plot T minus T naught, that is easier. If I plot T minus T naught, okay, versus z, this goes to 0 on both walls because T is equal to T naught, and at the center it has a maximum. Okay. T max is equal to the temperature at z is equal to h by 2. Okay. Substitute z is equal to h by 2 in this expression and you will get the maximum temperature as T naught plus mu v square by 8 k. Okay. So, this temperature is equal to mu v square that is the temperature. Okay. Now, we can calculate the heat flux. Okay. q z is equal to minus k partial t by partial z. Okay. This is a function of z, okay, because I have to differentiate this in order to get what is q z. Okay. So, this will be equal to the derivative of the first term here, the constant temperature will be 0. The second term, okay, it has a dependence on z and z square. So, I will get mu v square into h minus z by 2 k h square, differentiating using product rule. Okay, that is the derivative of the first z term. Then I will get another minus mu v square z by 2 k h square. Okay. I should have a negative sign here. Okay, so minus k into this whole thing. Okay, minus k into the derivative. So, first I differentiated this first z here, then I differentiated the second h minus z. When I differentiate h minus z, I get a minus 1 factor. Okay. So, this is equal to minus mu v square into h minus 2 z, okay, by 2 h square. Okay. The thermal conductivity will cancel out in this case. Okay. Okay. Now, this if you plot, this is okay. So, let me plot it in the channel here. Okay. The temperature profile we saw was a parabolic profile. T is equal to T naught at the wall, and at the center T is equal to T naught, okay, plus mu v square by 8 k. Okay. The heat flux, okay, q z, okay, that is going to be a linear profile. Okay. You can see that it is a linear function of z. Okay. It is going to be positive if h is less than 2 z. Okay. So, above the center line it is going to be positive, and below the center line where h is greater than 2 z or h is or z is less than h by 2, it is going to be negative. Okay. So, you have heat flux going upward on the upper half of the channel, going downward on the lower half of the channel. Okay. Okay. What is the total heat transfer rate out of the walls? Okay. The total heat transfer rate out of the wall, the outward heat flux, at the top wall, okay, is going to be equal to is q z at z equals h, okay, is equal to mu v square by 2 h square. Okay. This is the flux going upward at the top wall. Okay. Okay, that flux is going in the positive z direction, okay, because it is positive. Okay. Outward heat flux at bottom wall, q z at z equal to 0 is equal to minus mu v square by 2 h square. Okay. That heat flux is going down at the bottom wall. Okay. So, these are the fluxes at the top and the bottom walls due to the viscous heating. So, now this is the total heat that is generated in the channel is equal to the flux going out through both of the walls. Okay. So, therefore, the flux going out through both of the walls is mu v square by h square, that is the total amount of heat going per unit area per unit time of the walls. Okay. Now, we can calculate a Nusselt number for this. Okay. So, if I had a heat transfer problem, okay, I would take the Nusselt number as okay, Qz by K delta T by H. Okay. For each wall, this Qz is equal to mu v square by 2h square. Okay. So, this is equal to mu v square by 2h square into 1 over K delta T by H, is equal to mu v square by 2 K delta T, where delta T may be any applied temperature difference. Okay. So, if you solve this problem for difference in temperature between the fluid and the wall, that delta T is the applied temperature difference. In this case, it should just be taken as the temperature difference between the center and the wall. Okay. This temperature difference between the center T is equal to T naught and T is equal to T naught plus mu K square V. Okay. Recall that this is equal to the Brinkmann number. Okay. When we had done the heat transfer problem, we had expressed the Brinkmann number is equal to mu v square by K delta T. Okay. So, for this particular case, the Nusselt number is related to the Brinkmann number. When we had solved the original problem, okay, when we had solved the original problem of heat transfer, dimensional analysis to find out the Nusselt number correlation, in that case we had said that if there is no interconversion, then this Brinkmann number is not a factor. When there is interconversion, the Brinkmann number is a factor, and that Brinkmann number we had derived by dimensional analysis as mu times velocity square by K delta T. Okay. So, if that Brinkmann number is a factor, that is, if the transport of energy, the rate of transport of energy due to viscous heating, okay, the rate of generation of energy due to viscous heating and its transport through the walls is comparable to that due to heat conduction, then the Nusselt number will depend upon the Reynolds number, the Peclet number, the length ratio, and this additional factor, the Brinkmann number. This is a problem where the rate of where the energy conduction is entirely due to the viscous heating. Okay. So, if energy conduction is entirely due to viscous heating, then the Nusselt number is equal to Brinkmann number divided by 2 for this particular case, okay, where there is a linear shear flow between two surfaces. Okay. So, that is how we get the energy production rate due to viscous heating. This is a uniform source. Okay. This is a uniform source because the energy source does not depend upon position. Okay. The energy source does not depend upon position. So, therefore, this is a uniform source at steady state, okay, and this is the problem that we have solved, uniform source at steady state. In this case, since the second derivative of the temperature is proportional to the negative of the source, the temperature becomes a quadratic function of the position z. When there was no source, it was a linear function. In this case, there is a constant source, it is a quadratic function. Okay. And this is how we determined what is the temperature field due to this source, in this case the thermal source, and from that we had calculated a relationship between the Nusselt number and the Brinkmann number. Okay. In this case we had calculated the relationship between the Nusselt number and the Brinkmann number. I should note that at steady state, okay, at steady state if the source is some function of position, okay, then the equation that I get will be K d square T by dz square plus this energy source which is a function of z, that is equal to 0 if it is a function of z. Okay. In that case, partial square T by partial z square is equal to minus S E of Z by K. Okay. And I just need to integrate the source 2 times to find out what is the temperature profile. Okay. So, that is a procedure that we will use for finding the temperature profile. Just integrate the source 2 times. Okay. When you solve the second order differential equation, you will get 2 constants of integration, and those 2 constants of integration are defined at the 2 boundaries. Okay. And using that you can find out what is the temperature profile. Okay. Note that while doing this, we have assumed the diffusivity is a constant. Okay. While doing this, we have assumed that the diffusivity is a constant. Even if the diffusivity is not a constant, the equivalent equation in this case becomes partial by partial z of q z is equal to minus S E, which means that q z is equal to minus S E times z. Yeah, I made a sign mistake here. So, let me write the equation. Okay, this is equal to 0 at steady state. Recall, for unsteady, rho Cp times partial T by partial T is equal to minus partial Qz by partial Z plus Se, which means that partial Qz by partial Z is equal to Se. Okay. And I can integrate this once to get Qz is equal to Se into Z plus a constant A. Okay. So, even if the thermal conductivity is not a constant, the heat flux is still a linear function. If the source is a constant, the heat flux is a linear function of Z, even though the thermal conductivity may not be a constant. If in addition the thermal conductivity is also a constant, or the diffusivity is also a constant, then the field variable becomes a quadratic function. Okay. So, that is for a steady flow in the steady transport in the absence of sources and sinks. We will examine another example of this in the next lecture before we proceed to examining cases where the diffusivity is not a constant. Okay. So, I will continue this in the next lecture. I will see you then.